In this video, I'd like to introduce the fundamental theorem of calculus. The first version, it has two versions, not the fundamental theorem of calculus 1 and fundamental theorem of calculus 2. So in the books, we put the fundamental theorem of calculus 1 first because that's something that can be proven first, and then based on that, we can prove the second part. So the first one is proven from scratch using the definition of the integral. So just to remind you, the integral from a to b of f of x dx is the limit of the sum of f of xi star times delta x I from 1 up to n as n approaches to infinity, where the xi's are the boundary points of the partitioning. So a is x0, then you have x1, then you have x2, then you have xn, which is b. And in many cases, in many calculus 1 classes, we take delta x to be of equal size, b minus a over n. Okay, so there will be n subintervals of equal size, and then we pick xi star from the ith interval. So provided this limit exists, meaning we make more and more finer and finer partitioning, we get to the limit goes to a particular fixed point, finite value. We say the integral exists and the function is integrable. So this notation stands for this limit. Well, here's the thing. If we have a graph of a function, and if the graph happens to be above the x-axis, that notation gives us the area under the graph of the function. So this calculation gives us the area. The area is not the definition of the definite integral. I lost my pen. Okay. So the area is not the definition, but it's a result. It's something that we get from computing that stuff. Okay. So on the other hand, if we have a function that goes above and below the x-axis, then this integral gives us the net area, thinking this as positive areas and this as negative area. We add them up, and that gives us that net area. If the function is a velocity function, this gives us the displacement. And there are other uses you will learn in calculus 2 also. Now, remember, so having this reminder, now what if we want to calculate the integral? Let's say this is a t-axis. Let's say it's from a to b. And let's say we have the function y given as a function of t. Okay, so we can do the integral from a to b of f of t dt. However, somehow we decide to put a point x from a to b. And instead of calculating this whole integral, let's say we calculate the integral from a to x of f of t dt. So in the continuous function case, what we're doing is we're calculating this area. The function is continuous and above the x-axis. This will give us the integral from a to x, gives us the area. Now if you move x over to the right, you would be changing the area. Or if you move the x over to the left, you would be changing the area. So this is a function of x. You can call it g of x. So as x changes, this value changes. That's why it's a function of x. You can call it g of x. So for instance, g of a is 0, because g of a is the integral from a to a of f of t dt. This is just an example, okay? or g of b is the whole integral from a to b. Okay, yeah. So different values of x give us different values of this integral. So call it g of x. Okay. Now, what the fundamental theorem of calculus, the first version, is saying that this function is actually differentiable. We actually know the derivative of this function. The function g is differentiable. And not only that we know it's differentiable, we actually know the derivative of the function. G prime of x is actually just a function, replace t by x, and whatever you see in this expression, that's what it is. So that's the theorem, all of it. So this function is differentiable, and the derivative is f of x. So let me write this again, okay? So suppose f is integrable on the interval ab. Suppose that integral exists. Now define g from, so g is defined from ab, okay, into r. So g is a function given by g of x equals the integral from a to x of f of t dt. Okay? Then g is differentiable, and the derivative of g is just a function f. Okay? In other words, if you differentiate the integral of a function, you integrate the function, a is not that relevant. It's just that the function must be integrable from a to b. So a part, the number a, you could start from 0, you could start from 1, any value, so long as the function is integrable from a up to x. Then take the derivative with respect to x, will give you f of x. Okay? So in the next, let me give you just a quick example. If you do the derivative of the integral from 0 to x of sine t dt, it's just simply sine x. That's all. That's what this is saying. And this is a quick example. Okay? So in the next three videos, I'll put 3 different examples using properties of the integrals and this this theorem. Okay? And these are very different examples. They're very important examples. So I'll just put a few examples.